Okay, before diving into more complex topics, it's worth stepping back and take a look at why computer simulations are so important. So in this video we're gonna explore a famous problem in probability, one that has baffled countless people, which is why many consider it a paradox, the Monty Hall problem. But why do yet another video? There's this problem has been debated ad nauseum. So why? Well, there's a part of the story that has been neglected, and that's what we're going to look at it. Uh, we're going to look at it through the lens of computation, and there's a lot that this method reveals. So let's go to the beginning. So in case you don't know the problem, this is the canonical description. Suppose you're on a game show and you're given the choice of three doors. Behind one door is a car, behind the other goats. You pick a door, say number one, and the host, who knows what's behind the doors, opens another door, for example number three, which has a goat. He then says to you, do you want to pick door number two? So the question is it to your advantage to switch your choice? So this basically is like this. You pick number one, the host opens number three, and now the question is, do you switch to number two or do you stay in number one? That is the problem. So if you have not encountered this problem, then pause the video and think it through. It's a very important problem, but most people already know the solution. So this is one answer. Yes, you should switch. The first door has 1/3 chance of winning, but the second door has 2/3 chance. So Marilyn Vos Savant provided this answer, I believe in 1990. So she's a columnist, and somebody asked this question, and that was her answer. But let's look at is it right, is it wrong? Let's look at the responses that she got. May I suggest that you obtain and refer to a standard textbook on probability before you try to answer a question of this type again. Charles Reed, PhD, University of Florida. So Marilyn didn't even finish university. So maybe she's wrong. Here's another response. I'm sure you will receive many letters on this topic from high school and college students. Perhaps you should keep a few addresses for help with future columns. Another PhD, Georgia State University. So it's not looking good for Marilyn. I am in shock that after being corrected by at least 3 mathematicians, you still do not see your mistake. Dickinson State University. Maybe women look at math problems differently than men. Okay. You're the GOAT. Western State College. So these are the responses that she got. But I want to focus on one particular part of the story, which is uh, what Paul Erdos, um, hopefully I'm not butchering that. So he was one of the greatest mathematicians of the 20th century. Many considered him an expert in probability theory and, without a doubt, one of the most prolific in history. So, what did he say? He said, "No, that is impossible. It switching should make no difference." Okay? But this was in a conversation with his friend Bar Shonyi. So he initially remained unconvinced that two-thirds was the correct solution, even when his friend and fellow mathematician explained it using decision trees and Bayes' theorem. Then Shonyi had the idea of showing him a computer simulation, and that's where the interesting part starts. Okay, so the Monte Carlo method was well known to Erdős because it was first introduced by his good friend and collaborator uh, Stanisław Ulam, a mathematician who played a major role in the development of the hydrogen bomb at Los Alamos. So, what was this simulation? So, I researched the description of how this simulation looked, and it was something like this. So, we're gonna follow the stay strategy. So, first we pick door number 1, and then we're gonna stay in door number 1. The host opens uh, one of these two doors. This case is door number 2, and then, well, we're always gonna stay in door number 1, and let's see what happens. So in this case, we won. The car was on door number 1, and the host is crying because now he has to pay a car to us. So this keeps a tally of how many times the host cries or smiles. That's how Bakshini developed the simulation, at least according to him. So once again, we're gonna stay in door number 1. Host opens door number 3. So the car is either in door number 1 or door number 2. Let's see. All right, this time we lost and the host smiles, so now it's 50-50. We can continue doing this. This is random number generation. We lost, the host smiles, 2 smiles, 3 smiles, now 1 cry, and so on. It's just a simulation using a random number. Let's get another cry. So now it's 6-2, 7-2, 8-2. Let's get another one. Okay, we're just losing and losing and losing. 10-2, 11-2. All right, that was extremely unlucky, but from this, like, there's very little chance. It should be close to 33%. But okay, this is a computer, so we don't have to do this slowly. We can just automatically do it 100,000 times, which is what Bakshini did. And we get 67% of the time the host smiling, and we lose. So this is normal. No, nothing surprising here. But now let's switch the strategy to the switch strategy. All right? So we start with door number 1 again, but now we're gonna switch. The host opened door number 3, So we're going to switch to door number 2. So we won. The host cries. That's 0, 1. Okay, we switch again. 0, 2. We're going to switch again. 0, 3. Alright, 1, 3. And so on. 2, 3. We don't have to do this slowly. We can just do it 100 times. Actually, let's just open this. Alright, let's do it 100 times. And then this time he cries 66% of the time. So in the stay strategy, he smiles 2/3 of the time. In the switch strategy, he cries 2/3 of the time. So clearly, the switch strategy is better. And that's it. That there's no arguing. This is a computer simulation. Well, we'll see. But we don't have to do that step by step. We can use, this is the R programming language, as we have been using in this series. And what we're going to do is just generate all the data. It's extremely easy. So car contains a random number between 1 and 3. For example, let's see how many times is the car in the, well, 33% of the time in number 1, 33 in number 2, 33 on number 3. Okay. Then the host is gonna pick door number 2 or door number 3 based on where the car is. But okay, so that's the host, and then our choice is gonna be the other door. So if the host pick door number 3, then we pick door number 2, and so on. So if we add these two, it's always 5, right? He picks 2, we pick 3. He picks 3, we pick 2. That's it. So let's just plot this. This is what we have. If we use the stay strategy, 33%, we win 33% of the time. If we use the switch strategy, 67%. So that's it. That's another confirmation that using a computer simulation that the switch strategy is twice as better as the stay strategy. But I want to look at this part of the code, because that's when you program the problem, some things some things pop up. So first we start with this 5 minus car. So car is gonna be 1, 2, or 3. So why do this? If the car is in door number 2, we're gonna pick, the host is gonna pick door number 3. If the car is in door number 3, he's gonna pick door number 2. But what is this for? There's no door number 4. Well, if the car is in door number 1, that's when we get this 4. So the car is gonna be 1, 2, or 3, and then 5 minus that is 4, 3, 2. So that switches 3 to 2 and to 3. But what do we do about this 4? So that's where the tricky part becomes apparent, because if the car is in door number 1, then the host can pick either door number 2 or door number 3. It's the problem doesn't specify what is the host going to do in that case, but because we're programming this, we need to make a decision. So this is the code that I used, but we can just say like, okay, if okay, if the host is equals number 4, so that's basically the same thing as when car equals 1. I wonder how if I can make it like this. Yeah. So these are the same thing. So actually I can do this like this. When the car equals 1, then the host is gonna pick door number 2. There we go. So let's see that door number 2, and then continue with the rest of the code, and it doesn't change anything, right? The host can pick door number 3 instead. Doesn't change. So it doesn't really matter, like if the car is in position number 1, the host can choose door number 2 or door number 3. Doesn't really matter. But those are the kinds of decisions that you have to make in the code. He has to he has to pick something. In this case, what this code does is like, this is gonna be where the car is number 1. So we chose 3 in this case, but we can pick some random number between 2 and 3. This is more appropriate, but it doesn't, as we saw, it doesn't really matter. Either way, a decision has to be made. In this case, we're gonna just pick randomly between 2 or 3. Anyway, so that's the computer simulation using R, and we get the same result as in this step by step. So that's the simulation. Now, Erdos objected that he still did not understand the reason why, but was reluctantly convinced that I was right. That was after he was shown the computer simulation. Eventually, Erdos realized why this was the correct, understood the reason why, but that was later on. Anyway, so this is another way of understanding the problem, but this is not necessary because the computer simulation already showed the true correct answer. So in this case, instead of 3 doors, we have 100 doors. Once again, we pick door number 1. It doesn't really matter, but that's the easiest to see. And the host, for some reason, is gonna open all of these doors except this one, door number 77. So the problem is the same. Do you stay with your original choice, or do you switch? Now, to me, here it's obvious what's the correct answer, but for the people that do not see, the probability that the car is in door number 1 is 1%, because there's 100 doors, 1 over 100, 1%. Therefore, the probability that there is a goat here is 99%. And by complement, the probability that a car is here in door number 77 has to be 99% because it has to be either here or here. Maybe it doesn't, you don't even need that understanding because from the beginning the car has to be from either a, the probability that the car is between door number 2 and 100 is 99%. So if it cannot be any of these doors, it has to be on this one with the same probability, 99%. So from any way you look at it, uh, the choice is to switch. This I think is the easiest, the best way to try to look at it intuitively. Not that it's needed because with a computer simulation you already know the correct answer. But it turns out that was the explanation that Marilyn Bosavant gave in her initial response. This is what she said. Here's a good way to visualize what happened. Suppose there are a million doors and you pick door number 1. Then the host, who knows what's behind the doors and will always avoid the one with the prize, opens them all except door number whatever, 77,000 777,777. So you'll switch to that door pretty fast, won't you? Yeah, because the probability is basically what 99.999% or something like that. That the door is that the car is there. So that was her explanation. So that explanation was not sufficient for thousands and thousands of people. So although probability seems easy superficially, it's not. The Monty Hall problem is a testament that even the greatest probabilists can get simple problems wrong. Fortunately for us, we don't need any of those advanced tools like Bayes' theorem or probability trees. We can just use computer simulations to find the right answer, even if our intuition is wrong. So, in the end, Vasavant was right. She was proven right. She challenged, after many multiple attempts at explaining the problem, she challenged people to just do this by hand. I think it was 200 rounds. Somebody is the host, somebody is the contestant, and just do it. The magazine received thousands of letters, and of the people who performed the experiment by hand as described, the results are close to unanimous. You win twice as often when you change doors, which is expected. Nearly 100% of those readers now believe it pays to switch. Everyone except one 8th grade math teacher who, despite data clearly supporting the position, simply refuses to believe it. But also another part of the story is that many people, instead of doing the experiment by hand, did it with computer simulations. And most of them, I mean, some of them programmed it wrong, but most of them got the right result. So that's it. Simulation is better than intuition. So that's what we're going to use to explore the more complex topics. This is one of the simplest problems that intuition just fails, but simulation succeeds easily. And the coming problems are not going to be that easy, but we're just going to use simulation and the result is going to be the same. We're going to get the right answer every time. So if you find this useful, leave a like. Cheers.